Hello, everybody. This is just a short welcome to say hello and welcome to semester 2 of calculus in first year mathematics, MA 180, MA 186, MA 190. So you're all very welcome back. I hope you had a break over Christmas and looking forward to working with you very much in semester 2. So this is really just to say hello and give a short indication of what to expect, what our way of working together will be. As my name is Rachel Quinlan. I'll be lecturing the calculus section in semester 2. And our plan basically is that we have the times that are allocated to us for lectures are Wednesdays and Thursdays at 10 o'clock. So we'll run lectures via Zoom at those times. And you're more than welcome and strongly encouraged to participate in the Zoom meetings at those times if it's convenient for you. If it's not, the lectures will be recorded and they'll be uploaded to the course website. Okay, so you're welcome to get in contact with me at any stage. My email address, rachel.quinlan@nuigalway.ie. So just to say, obviously this is not the way that we would like to be conducting our lectures this semester. Unfortunately, with the public health situation being the way it is, it's likely to continue in Zoom for the whole semester, and our opportunities for in-person interactions are unlikely to really arise during the semester, which is very regrettable. On that note, I want to really congratulate all of you on your resilience and on your tenacity. This is not the introduction to university education that we would have liked you to have, and probably not what you would have wished for, certainly not. So I just want to say, well done on being here and on your perseverance. It's not an easy way to start your third level education, and we do understand that. A few words about what we'll be doing in this course in terms of the mathematical content. So to an extent, it picks up from work that you've done already in semester 1 with Graham, but there are also some new elements that don't particularly directly relate to that. So basically, the way our course in calculus will be structured is there'll be 3 chapters. The first chapter is about integration, which is really kind of a direct progression from semester 1's content. And the other 2 chapters will be about 2 other topics. So let me just say a little bit about what each chapter entails and what kind of questions and answers we'll be looking at in each chapter. So chapter 1 of the lecture notes is called Integral Calculus. It's about integration. If you haven't encountered the term integration before, it does 2 things. On the one hand, integration is sort of the reverse process of differentiation. So kind of the basic problem of integral calculus, on the one hand, is here's a function. Find something that has that function as its derivative. And we'll be looking at that, and we'll be looking at some techniques for solving that problem, which in general is a very difficult problem, but there are techniques that allow us to get a certain distance with it, which we will look at. The question, though, of why you might care about such things is kind of the more interesting one in a way. So, why is it useful to be able to figure out something that has a given derivative? Well, at least a partial answer to that is that it turns out to be useful for answering lots of questions that arise in applications. And in particular, it turns out to be useful for the problem of calculating the area of a region that is bounded by the graph of some known function, which often turns up in applications because it essentially arises in connection with sort of trying to calculate totals of some sort of continuous processes. And I'll say more about that as we study the lecture notes in chapter 1. But it's a problem that does arise in lots of applications to different areas. And the fact that it's connected to the theory of differential calculus is something that's not obvious at all, that in a way brings a lot of extra power to calculus. And the connection between those 2 problems, calculating the area under some curve and the problems of differential calculus, rates of change, and so on, is captured by something called the fundamental theorem of calculus. And that'll be one of the highlights of chapter 1 of our lecture notes. So in chapter 1, a lot of our focus will be on practical techniques of integration. We'll have lots of examples to work on, lots of things to figure out. And our main kind of theoretical element in that chapter will be this fundamental theorem of calculus, which explains the connection between differential calculus and the problem of calculating areas under graphs. Okay, so we'll make all of that more explicit and more, obviously discuss it in a lot more detail in the first sections of the lecture notes. Okay, that's chapter 1, and that'll take approximately the first 4 weeks of the semester, basically a third of the course, and it'll also account for one of our 3 questions in the final exam, which I'll say more about obviously in due course. Okay, chapter 2 is about the real numbers. So calculus really is about studying the real numbers. And what we'll talk about in chapter 2 are some properties of the real numbers that distinguish the real numbers from other number systems, such as the integers and the rational numbers. So obviously, when we're talking about the real numbers, we have notions of continuity, differentiability of functions, integrability, which you don't necessarily have when you're working with other systems, such as the integers and the rational numbers. So We'll also talk about the question about whether the set of real numbers is a bigger set, for instance, the set of integers or the set of rational numbers. Now, all of these are infinite sets, so that might look like a question that doesn't even have a sensible answer, but it does have a sensible answer, although that answer is sort of fairly recent in terms of the history of mathematics that arose around the beginning of the 20th century. So we're going to talk about how people think about infinite sets, about how people think about infinity, about whether different infinite sets can be different from each other in terms of their numbers of elements. We'll discuss the concepts of countable and uncountably infinite sets, which arises in connection with that and which dates back to the work of Cantor in the late 19th century. So at the end of that section, you'll be able to talk about finite, countably infinite, uncountable sets of real numbers, and also explore concepts of maximum and minimum elements and related things for sets of real numbers. So it's a subtopic that kind of intersects almost the practice of real analysis and calculus and sort of philosophical questions in mathematics, such as how we deal with concepts of infinity. Okay, and chapter 3 then is something that kind of combines concepts from both chapter 1 and chapter 2. We'll be talking about sequences and about the concept of convergence. And here I suppose we'll talk about all the ideas here in much more detail later. But the kinds of questions that we'll be able to answer after studying the concepts of chapter 3 are things like, how do we calculate the value of pi? For instance, so pi, we know it as the ratio between the circumference and the diameter of a circle. We also know that it has a value, something like 3.14 or 22/7 or whatever. But we can't calculate the value of pi by looking at a circle. We can conceptualize the meaning of pi by looking at a circle. But we can really only do calculations with rational numbers, and pi is an irrational number. So how do we know its value? How are we able to calculate its value to some specified level of precision? And the answer to that really is that we're able to produce examples of sequences of rational numbers that have pi as a limit, that converge towards pi. And that's what we'll talk about in chapter 3, how we can basically use rational numbers to get at irrational numbers. And the same question arises in the context like, how do we calculate the value of the cosine of 3? Okay, the cosine of 3 is a number. Its definition is that it's the x-coordinate of a point that you reach by traveling the distance of 3 around the circumference of the unit circle. But how do we calculate its value? And the answer again is we get at it through sequences of rational numbers that converge towards it. So the machinery in chapter 3 is something that's of both theoretical and practical importance in mathematics. So we'll be discussing the concept of convergence for sequences and also hopefully a little bit about its usefulness. So that's just a very kind of rapid introduction to the 3 topics that we'll be talking about in this course. So don't worry if it doesn't all mean an awful lot to you yet. It will hopefully once we get into talking about these topics. The way that the assessment will work in the course generally will be, we'll have our weekly workshops, which will commence in week 2. We'll have, as in semester 1, a sequence of homework assignments, which will operate on the Alkizon system. And we will also, differently from semester 1, have an official end of semester exam in the formal semester 2 exam session. And that'll have 6 questions, 3 from the algebra side and 3 from the calculus or analysis side. And in the calculus side, each of the 3 questions will correspond to one of the 3 chapters of our lecture notes. But we'll say more about that later. This is really an introduction to say hello. So our first lecture will be on Wednesday, the 10th of February at 10 o'clock on Zoom. Every week on Tuesday, the Zoom links for the meetings will be circulated at the same time as a sort of weekly update with kind of a preview of what's coming up each week. Okay, so see you on Wednesday. Thank you very much, everybody, and looking forward to working with all of you. Good luck. Bye-bye.